Hello, today we're going to be talking about metals, and we're going to start off by looking at the periodic table of elements, and it has different groupings of elements that we're going to go through. So these elements are basically, there's 92 natural elements, and the scientists and engineers have managed to create an additional 28 other elements that are all have a molecular weight greater than 92 atomic mass units, and all of those are radioactive. And we've come a long way since Aristotle's theory of everything existing as either air, water, fire, or earth. We now know that all objects are made out of one or more elements. These elements, where did they come from? Well, the universe is made up primarily of hydrogen and helium, and then stars will actually, compress and convert hydrogen into helium, and then later on in the lifetime of the star, it'll start to compress helium into other things. Eventually can create iron and all of the other elements on the periodic table. Most of those occur during supernova explosions, when the pressures and temperatures reach astronomical limits, and that's when these atoms are actually fused together. So the beauty thing about the periodic table is that you can get a lot of information about an element from where it happens to be located on the periodic table. And understanding that basic plan will help you infer some basic information about each of the elements along the way. So what we have here is we have nonmetals. On the periodic table, they're shown here in green. We have the metalloids, which are shown in purple, and then everything else is considered to be a metal. So here are some examples of different types of metal. Here we have nickel, which has an atomic weight of 28 grams per mole. Rubidium, which is heavier. Copper, which is 29 grams per mole, and gold, which is extremely heavy at 79 grams per mole. And so what do these properties have? So first of all of these metals that we're talking about are left of that black zigzag line that we have here on the periodic table of elements. And most of these elements are solid at room temperature, with very few exceptions. So what properties do these metals have? Well, metals have luster, and that means that they're generally shiny in their elemental form. If they oxidize, say you have iron that is oxidized, it turns to rust, it loses its sheen and its shininess and its luster. These metals are also ductile, which means that you can draw them into a wire by essentially pulling on the atoms. And these metals are also malleable, which means that they can be hammered into thin sheets. Gold is particularly malleable, and it can actually be hammered down and flattened out to just a few atoms thick if you wanted to do that. And that's one of the things you may be familiar with. It's called gold leaf, which is a really, really thin layer of pure gold, which you can use to gild objects and make them look like they're made out of gold when they just have this very, very thin layer of gold. So the other thing about metals is that most of these metals have a high melting point. Obviously, mercury is liquid at room temperature, but something like titanium has a melting point that's more than 2,000 degrees Celsius, and that's why it's often used in aerospace applications, high-speed applications where the metal will get very hot. Metals also tend to be very dense, which means that they have a lot of weight in a small volume, but there's a wide variability in the density of the metals. Aluminum has high strength but low density, and that's why it's used commonly in aircraft. And titanium, which is much more expensive than aluminum, is stronger than aluminum, but also weighs significantly less. And so for aerospace applications where strength and weight are issues, you'll often go for the higher expense of using titanium. So these metals are also generally conductors, which means that they can allow for the passage of both electricity and heat through them readily. And the other thing about most of these metals is that a lot of them will actually react with water or oxygen, and this results in corrosion and rust. Essentially, it's an oxide coating on the outside of the metal, corroding the metal. There are very few metals that don't undergo any corrosion. One of those happens to be gold. Gold artifacts, when you dig them up from the ground, or if you find them in the bottom of the ocean, essentially look as good as they did when they were buried or lost at sea, because they do not corrode for gold. The same is not true for silver and other precious metals. Then we have the nonmetals. Here's some examples of nonmetals. We have sulfur, which is yellow. We have nitrogen, which is a gas in this case. We have selenium, and we have bromine, which is a gas as well. So these nonmetals occur to the right of that zigzag line, and some of them, but not all of them, are gases, but many of them are. And hydrogen is the lone one over on the left. So what are the properties? Well, unlike the metals, most of the nonmetals are dull in luster. They're not shiny. They tend to be brittle. That means that if you basically apply force, they will crack and break into pieces. And because of that fragile nature of the nonmetals, they're also not ductile or malleable. You can't turn them into wires, and you can't hammer them out into thin sheets. They just crumble under the pressure. They also tend to have a low density, so they don't have a large mass in a small volume, like the metals. And they also tend to have low melting points. So for some of these, say for example, like oxygen, it's definitely a gas at room temperature. You have to cool it to a very, very cold temperature in order to get it to condense into liquid. Same thing is true for hydrogen or helium or nitrogen. These nonmetals are also poor conductors of heat and electricity. They don't have electrons that are readily available for moving electricity. And then we have the metalloids, which exhibit properties kind of both nonmetals and metals, depending upon which metalloid you're talking about. So here are some examples: germanium, silicon, which happens to be the most abundant element on the surface of the planet. We have polonium, and then we have arsenic. So these metalloids are right along that zigzag line over on the right, and they have properties that are both metalloids, or both metals and nonmetals. They have some of those properties. So some of them are like boron. Here is another one that has properties of both metals and nonmetals. For example, some of them are shiny with luster, in this case antimony, and some of them are dull, in this case like silicon. Recall that one of the primary uses for silicon is actually the generation of silicon wafers, which are the base plate for computer chips and also the base plate for photovoltaic cells for solar power generation. These metalloids generally do conduct electricity and heat better than nonmetals, but not as well as metals themselves. And some of them are malleable and some of them are ductile, really depending upon. So these elements can be really categorized into periods, which are your horizontal rows. Elements in a period do not have similar properties. You can't look at the periodic table in a horizontal way and gain much information about the properties of the elements themselves. Instead, we look at elements, we divide them into families, which are grouped vertically in columns. And all the elements in families have similar properties. And the reason for this is that they have a similar valence electron structure. And by valence electrons, we're talking about the outermost electrons. So these families, they all generally behave in the same way because they have kind of a similar affinity for their outermost electrons. And so, for example, most of these metals have 3 or less valence electrons in their outer shell and are therefore likely to lose those electrons into chemical bonds. And those electrons are actually fairly mobile, being able to move from one metal atom to another through the flow of electricity. And for nonmetals, most of the nonmetals have 5 or more valence electrons and are therefore usually trying to gain electrons to complete their outer shells. And so here you have an example of sodium metal, which is donating an electron to chlorine, which is a nonmetal, creating a mineral, sodium chloride, which is basically table salt.